Welcome to a read along with Dr. Powell in the book Discrete Perspectives in Mathematics. This is subsection 6.4.2. Okay, so remember how we talked about how a matrix, thought of as the variable x, has a minimal polynomial that makes it zero. So that polynomial behaves like zero. Well, x to the fourth, what if we want to take a power of this matrix, like x to the fourth? X to the fourth is a polynomial, and um, and if we and x squared minus 3x minus 4 is behaves like zero, and the idea of making that behave like zero is preserves operations, which means it's like modding. So really, in order to compute x to the fourth, all we need to do to make it simpler on ourselves is to take x to the fourth mod that polynomial, and the result will be the same. Wow. I mean, to compute x to the fourth, we don't have to raise it to the fourth power. We can look at even a simple representative in this mod. Here, we can do a polynomial division here, and we look at the remainder, 51x plus 52. That's the remainder, and it is a simpler representative of, um, of x to the fourth in this mod. So to compute that power, x to the fourth, all we have to do is just compute this polynomial. So 51 times the original matrix plus the scalar 52, but behaving like a matrix when we have an outside multiplication, 52 on this diagonal, we add that together, and look, we get a to the fourth right there. Um, okay, so one little thought um, right here. So this matrix was one we were already considering that had that minimal polynomial. How do you get a minimal polynomial in general? Well, um, row and column operations can always be used to get a matrix down to a diagonal matrix without changing the determinant. Okay, so don't change. Don't change the determinant if you just do sliding. Okay, just kind of slide it around, and and actually at that point, taking the product of the diagonal at once it's a diagonal matrix and zeros on the off diagonal is actually equivalent to the determinant of that matrix up to a factor of plus or minus one, which me and that determinant, since this is like since this matrix is behaving like a zero multiplier, that determinant should be zero, right? Which means the minimal polynomial actually is a divisor of the determinant. So even though you don't know the minimal polynomial, you can at least divide out, you can at least mod out by that guy, and it'd still be okay because you already know it's going to be zero. The determinant is a polynomial multiple of the actual minimal polynomial, so it will be zero. So we can mod out by it and still be accurate. So what we can do is to get that zero multiplier, all we have to do is like say x behaves like a. So x minus a as a matrix is a zero multiplier. Take its determinant, and we have a polynomial we can mod out by. For instance, if we have this matrix right here, we have x minus a. So thinking of x as being on four diagonal zeros on the offset, and you subtract, you get this matrix, and you take its determinant, so this way minus that, you'll get a polynomial which will behave like zero. Minimal polynomial divides it. So meaning we can mod out by it. So if we want to compute x to the fifth, we just simply take a representative of x to the fifth mod uh, x minus 2x plus 3 like this. And we can use our technique that we had before from a previous section in the book of how to find a simple representative of x to the fifth. I'll let you look through that. And finding that simple representative, we plug in a and we have the scalar, and we get that high power. And we'll end this little read along right here. Thanks for watching.